La presencia del doctor Carlos Arámburo de la OS, coordinador de la investigación científica de la UNAM. También está el doctor José Francisco Valdés, Galicia, director del Instituto de Geofísica. El doctor Federico Greff, director general de CICESE. Y el doctor Ismael Herrera, decano del Instituto de Geofísica. Vamos a iniciar con unas palabras del doctor José Francisco Valdés.
Quien nos hizo favor de hacer las presentaciones, desde luego, es el doctor Jorge Zavala, jefe del Servicio Mareográfico Nacional. Muy buenos días a todos. Doctor Carlos Arámburo de la OS, coordinador de la investigación científica. Doctor Federico Greff Ciel, director general del Centro de Investigación Científica y Educación Superior de Ensenada. Doctor Ismael Herrera Revilla, investigador emérito, exdirector y decano de este Instituto de Geofísica. Doctor Jorge Zavala Hidalgo, jefe del Servicio Mareográfico Nacional. Distinguidos funcionarios de la Secretaría de Marina y del CENAPRED, que hoy nos acompañan, gracias por estar con nosotros. Compañeros directores y directoras, o debería de decir directoras y directores, de la UNAM. Académicos, estudiantes, trabajadores de esta universidad, amigos todos, bienvenidos a Tlayolotl, bienvenidos al corazón de la tierra. Me ha tocado hoy el privilegio de iniciar este evento que celebra los 60 años de funcionamiento ininterrumpido del Servicio Mareográfico Nacional, cuya sede ha sido este Instituto de Geofísica. Otro servicio más que la UNAM brinda al país, atendiendo a su carácter de nacional, reafirmándose con ello como una de las instituciones señeras de nuestro México. Felizmente, hoy colaboran con nosotros en estas tareas muchas instituciones públicas, proporcionando facilidades para la infraestructura o siendo parte integral del servicio al hacerse cargo de las estaciones en regiones enteras de la costa mexicana, como el CICESE, cuyo director general hoy nos acompaña y hará un recuento de las tareas que el CICESE hace para el servicio mareográfico. Los antecedentes más antiguos de mediciones formales del nivel del mar son aquellas que la UNAM realizó a finales de los años 40 del siglo pasado, en colaboración con la Secretaría de la Defensa Nacional y el Servicio Geodésico Interamericano, para apoyar la elaboración de la carta respectiva a escala 1 a 500,000. Una vez creado el Servicio Mareográfico Nacional en 1952, fue posible conocer el tipo y rango de mareas en México, lo cual ha sido fundamental para la operación de puertos y construcciones en zonas costeras, para determinar el nivel medio del mar e indispensable para la cartografía nacional. Digno de señalarse es uno de los esfuerzos internacionales relevantes en los que participó el Servicio Mareográfico Nacional y que fue el realizado en los años 80 para monitorear el fenómeno de El Niño, que tuvo como resultado la capacidad para pronosticar este fenómeno. La información de la variabilidad del nivel del mar ha permitido apoyar el desarrollo del conocimiento de la dinámica del Pacífico tropical nororiental y del Golfo de California. También se han monitoreado muchos eventos de mareas de tormenta, tsunamis locales y remotos, algunos de los cuales serán reportados posteriormente por el doctor Gerardo Suárez. El registro de los cambios del nivel del mar debido a la variabilidad interanual natural y a las tendencias de largo plazo asociadas a fenómenos locales y al cambio climático reviste particular importancia. La riqueza y posibilidades de utilización de las bases de datos generadas por el Servicio Mareográfico Nacional es amplia. Sin embargo, estas aún esperan ser analizadas para profundizar en el conocimiento de los fenómenos señalados y otros de los que hoy conoceremos. De manera importante los sismos lentos, de los que nos hablará el doctor Costoglodo, y algunas otras posibles aplicaciones que oiremos de labios del doctor Krishna Singh. Algunos años atrás, el Servicio Mareográfico Nacional vivió una profunda crisis. Había muy pocas estaciones operando y los recursos disponibles eran escasos. Enfrentamos entonces la disyuntiva de cerrarlo o hacer un esfuerzo para renovarlo. Para tomar la decisión se convocó a un grupo de académicos especialistas de varias instituciones, con quienes se discutieron ampliamente las alternativas posibles. La conclusión de las reuniones fue que era importante que la UNAM continuara midiendo el nivel del mar, pues poseía las series más antiguas de la medición de este parámetro, significativo para la historia de nuestro medio ambiente. En aquel momento, el Servicio Mareográfico Nacional contaba solo con el apoyo de un técnico administrativo y una secretaria. Para su consolidación, se apoyó al servicio asignándole 2 técnicos académicos, ambos ingenieros, uno con experiencia en instalación y manejo de equipo altamente especializado, el otro en cómputo y sistemas. Para ello, contamos con el apoyo de la Coordinación de la Investigación Científica, y al señor coordinador agradezco las gestiones que hizo para que esto pudiera ser posible. Recientemente hemos podido sumar personal administrativo que contribuye con los trabajos técnicos del servicio, señaladamente en la digitalización de los mareogramas. El presupuesto operativo y de infraestructura del Servicio Mareográfico Nacional ha partido siempre del presupuesto del Instituto de Geofísica. La modernización respectiva no ha podido pues avanzar al ritmo que hubiéramos deseado. Mantener una red nacional es muy costoso, reconstruirla es aún más. Afortunadamente, para la reconstrucción de las estaciones mareográficas hemos contado con el apoyo de diversas instituciones. En particular, quiero aquí agradecer a las administraciones portuarias, las APIs, de Ciudad del Carmen, Campeche, Progreso, Telchac, Isla Mujeres, Cozumel, La Paz, Puerto Vallarta, Salina Cruz y Puerto Chiapas, a la Escuela Náutica Fernando Silicio en Veracruz, a la Unidad CISAL del Instituto de Ingeniería y al CIMBESTAB Mérida, al Instituto de Ciencias del Mar, particularmente en Puerto Morelos y Mazatlán, al Club de Yates de Acapulco y a Fonatur en Huatulco. En el ámbito internacional, nos han auxiliado el Global Sea Level Observing System, GLOS, la Universidad de Hawái y la UNESCO. Mención especial merece la colaboración que hemos tenido con el Centro Nacional de Prevención de Desastres, el CENAPRED, las Secretarías de Marina, Gobernación y Comunicaciones y Transportes, el CICESE, con quienes se ha implementado el Sistema Nacional de Alerta de Tsunamis, cuyo personal directivo hoy nos honra con su presencia, a través del cual se nos han asignado recursos que permitirán continuar modernizando el Servicio Mareográfico Nacional y desarrollar una red más completa. También esperamos recursos otorgados a través del convenio que crea la Red Sísmica Mexicana, donde participan las secretarías e instituciones ya señaladas, junto con la UNAM. Aún cuando hoy podemos decir que hemos recuperado una red nacional de estaciones, 18 de ellas transmitiendo en tiempo real y otras 40 donde se tiene información histórica del nivel del mar, los sitios que hoy operan lo hacen con el equipo mínimo necesario para monitorear las variaciones del nivel del mar. Aspiramos a contar con sistemas autónomos de energía, con sensores de parámetros meteorológicos y algunos otros equipos que las hagan más robustas con mayores capacidades. Corresponderá al doctor Jorge Zavala, jefe del servicio, hacer la revisión y reporte de la situación actual y perspectivas del Servicio Mareográfico Nacional. A mí solo me resta hacer aquí patente a Jorge y al equipo que él comanda mi agradecimiento por su energía, por su tenacidad, por su versatilidad, por su espíritu de servicio, en fin, por haber recuperado para nuestra universidad, para nuestro país, la red de medición de parámetros ambientales más antigua que en él existe. Gracias.
A continuación vamos a tener unas palabras del coordinador de la investigación científica de la UNAM, el doctor Carlos Arámburo.
Muy buenos días, tengan todas y todos ustedes. Me da mucho gusto poderles acompañar en este importante acto que conmemora, sin duda, pues algo muy importante, el cumplimiento de 6 décadas de trabajo ininterrumpido del Servicio Mareográfico Nacional. Saludo al doctor José Francisco Valdés, director del Instituto de Geofísica, al doctor Federico Graef, director general del CICESE, al doctor Ismael Herrera, investigador emérito de este instituto, al doctor Jorge Zavala, responsable del Servicio Mareográfico Nacional, por supuesto a todas las directoras y directores del subsistema de la investigación científica que nos acompañan, a la coordinadora del Programa Universitario en Medio Ambiente, los directivos del CENAPRED, de la Secretaría de Marina, y por supuesto a todos los investigadores, académicos, estudiantes que nos acompañan de esta y de otras entidades académicas. 6 décadas, pues a veces se dice fácil, ¿no? Es 60 años. Habrá que remontarse a ver cómo estaban las condiciones en esos tiempos para ver el impacto de la visión que tuvieron esos pioneros que decidieron iniciar una tarea como la que ahora configura al Servicio Mareográfico Nacional y el impacto que a lo largo de estos años ha tenido sobre múltiples aspectos de la vida nacional. Por supuesto en la académica, en la formación de recursos humanos, pero también en la de vinculación y en la del servicio al país y a la sociedad. El Servicio Mareográfico Nacional, que como ya mencionó el doctor Valdés, tiene su sede aquí en la Universidad Nacional, en el Instituto de Geofísica, pues constituye un esfuerzo muy importante de los universitarios, pero también de otras instituciones y por supuesto, pues cuando queremos hablar de una red lo más integral posible es indispensable el poder colaborar con otras instituciones y coordinar los esfuerzos y los recursos para que esto funcione. Y ahí en muchas ocasiones reside justamente el quid para que estas organizaciones funcionen bien en los esfuerzos de articulación y de coordinación que se puedan llevar a cabo. Y me parece que desde la Universidad Nacional este es un esfuerzo que se ha manifestado aquí como en otras instancias, por ejemplo el Servicio Sismológico Nacional que también está instalado en este instituto. ¿Cuáles son las funciones primarias que tiene este servicio? Bueno, ya mencionó el doctor Valdés, es tener un registro constante, fidedigno, certero sobre el nivel del mar, el comportamiento de las mareas, el poder tener monitores y detectores en distintas regiones de el territorio nacional, particularmente, por supuesto, en los litorales, para saber cómo se está comportando este parámetro, que sin duda tiene impactos económicos muy importantes, que es vital para el desarrollo de varias actividades económicas, como la pesquería, por ejemplo, pero que tiene implicaciones también en la protección y en la prevención con relación a desastres, por ejemplo, causados por efectos naturales. Después, un servicio estratégico para el desarrollo del país y un servicio que debe de seguir siendo apoyado y sobre todo fortalecido. La universidad, consciente pues de su papel en la vida nacional, ha estado tras este importante servicio que, como mencioné, pues tiene múltiples facetas. Por supuesto, la posibilidad de realizar investigación, de generar conocimiento original, que es una de las principales actividades que tenemos en esta casa de estudios, la formación de recursos humanos especializados también en este tipo de efectos, y el de la vinculación con la sociedad. Y por ello es importante seguir fortaleciéndola, sí, desde la universidad, que bueno que en los últimos años se han podido canalizar algunos recursos, tanto humanos como materiales, al fortalecimiento de este servicio. Por supuesto, desde la UNAM seguiremos haciéndolo, pero es necesario potenciar también las interacciones con otras instituciones, y a través de estos ejercicios de articulación y de coordinación con otras instituciones, como ya se mencionó, con el CENAPRED, con la Secretaría de Marina, con los gobiernos estatales, sin duda es importante hacerlo. Me parece que el Estado mexicano como tal tiene una responsabilidad muy importante para generar mejores condiciones para el desarrollo de este tipo de servicios, el mareográfico, el sismológico, aquellos que tienen que ver con el estudio del cambio climático, con la cuestión del servicio meteorológico, en donde la universidad está sin duda muy comprometida, pero que requerimos un esfuerzo mucho más amplio y coordinado del Estado mexicano para hacerlos, porque en muchos de estos casos estamos hablando de asuntos de seguridad nacional, sobre todo cuando pensamos en cuestiones que tienen que ver con la protección o la prevención de desastres, con la posibilidad de, a través del conocimiento y de la anticipación o posibilidad de conocer de antemano algún efecto que va a suceder, como en el caso de los sismos y los tsunamis, y entonces poder desplazar a las comunidades, prever ciertas contingencias, pues esto es un asunto ciertamente muy importante. La UNAM, como ya lo describió el doctor Valdés, ha venido cumpliendo, como lo hace en muchos otros ámbitos, con esta responsabilidad, con convicción, con visión y ciertamente también con recursos a tratar de fortalecer a estas importantes actividades que se realizan en nuestra casa de estudios, y lo va a seguir haciendo, por supuesto. Invitamos y exhortamos a los otros componentes que pueden ayudarnos a fortalecer, a ir más rápido, a generar con un mayor dinamismo el robustecimiento de la infraestructura, tanto humana como material, que requiere, en este caso, el servicio mareográfico, pues para que sumemos esos esfuerzos y potenciemos nuestras capacidades, que hagamos sinergias y que esto tenga un mejor impacto sobre el servicio que le proveemos a la sociedad mexicana hacia ella. Quiero felicitar, por supuesto, a todos los académicos, a todos los integrantes del Servicio Mareográfico Nacional por este 60 aniversario de actividades, que sea esta ocasión una oportunidad, no solamente para revisar, como lo van a hacer a lo largo del día de hoy, pues qué es lo que ha sido, en dónde se está y cuáles son las expectativas hacia el futuro. Ha sido también una oportunidad para tratar de ver hacia adelante cómo seguir fortaleciendo a nuestro país a través de este tipo de acciones y a través de ellas pues la participación de la universidad. Una felicitación también al director de este instituto por su consistencia. Desde que yo llegué a la coordinación, uno de los temas que siempre se han venido tratando, no el único, debo decir, a todos los otros servicios y actividades también se le ha dado, pero en particular me parece que esta era una situación, digamos, muy sentida por el estado en el que se encontraba en algún momento y que había que tratar de fortalecer, de ampliar en colaboración con otras entidades académicas. Entonces, pues muchas felicidades a él, al grupo directivo que le acompaña en esta visión y por supuesto a los integrantes del Servicio Mareográfico encabezados por el doctor Zavala. Al Instituto de Geofísica, muchas felicidades también por estos 60 años de participación comprometida en su desarrollo y pues mis mejores deseos para que las siguientes décadas que sin duda vendrán del Servicio Mareográfico sean cada vez de mayor impacto para el país. Muchas gracias.
Del doctor Philip Woodworth, quien ha sido director por más de 10 años del Permanent Service for Mean Sea Level y ha sido también por más de una década el director de GLOS. Él ha sido director por más de 20 años del Permanent Service for Mean Sea Level. También ha sido director de GLOS por más de una década. Ha sido autor líder de todos los reportes del IPCC y es actualmente autor líder en el tema de nivel del mar. Y actualmente es revisor de la quinta comunicación, el revisor principal. Tiene varios libros escritos sobre el nivel del mar y una gran cantidad de publicaciones. Es probablemente el científico con más trabajo activo, el científico activo con más trabajos publicados con relación al nivel del mar. Y él nos va a dar la plática magistral el día de hoy.
Okay, first of all, I have to apologize for speaking in English, but I hope I can keep your attention for more than 10 minutes or something. And also, I'd like to thank very much the university and Dr. Zavala in particular for this inviting me here. It's a great pleasure and honor to come here on this important anniversary. So we're discussing sea level change and how to measure sea level and how to, important to predict long-term sea level change. Okay, what's the problem? The problem is that the coastal zone has changed enormously in the 20th century. The coastal zone has increasing populations, economies, and urbanization. Coastal areas below 10 meters contain 10% of the world's population. And there are at least 136 cities with over 1 million people, with a total population of 400 million people, and about 10% of them will be flooded in the next 50, 100 years. So it's a very big problem. There are places you can go in the world, like this is the Gold Coast in Australia, and in 1958 this was forest and simply a clean environment. Now it's full of hotels and billions of dollars of real estate. And this is in the path of very damaging storm surges, and this could be flooded very badly. So that's the problem. So this is a very big subject. Things I'd just like to mention today: how we measure sea level, how much sea level has changed? Do we understand why it's changed? A very important thing is, have extreme sea levels changed faster than the average sea level? Because the extremes are what floods your house. And look to the future in various ways. So one thing I like to do in a talk like this is to show you the sea level change in the last 500,000 years. And on timescales of maybe 120,000 years, sea level has changed by about 100 meters or so. There's always some guy in the audience who says sea level does not change. Okay, and sea level is the same as it was 100 years ago. But that's rubbish. It's because we don't live long enough. If we lived 1,000 years or more, we would see this big change of sea level. So what I'm discussing is here, in the last 100 years, the last 200 years, and it would be, the strange thing would be if sea level did not change, but sea level does change on all time scales. So how do we measure sea level change? There are two ways. We can use tide gauges, like the UNAM network at the coast, and we can measure from space using satellites. So the classical way to measure sea level is to use a simple instrument like this. This is the sea, and this is a tube, and in the tube you have a float. And the float goes up and down, the water goes up and down the same as the sea does. And as the float goes up and down, it has a wire that connects to, it connects to a computer these days, but in the old days to a chart. And so you can measure the water level change by a record on a chart. So the Mareograms that Jorge has here, he has a lot of these Mareograms, I think, that you want to process. So this is one of mine in Holyhead in the UK. We have two Stilling wells here, as you see. So that tube is these things here. But there are many other different ways of measuring sea level. These are other examples of the same technique. This is one of our tide gauges in Antarctica. If you go to Venice, you'll find many of them in Venice. But there are other ways. You can use radar to measure the sea surface. This reflects radar pulse off the sea surface and back. And also you can use sound. You can use acoustics to measure the sea level. You bounce an acoustic pulse off the water. So there are many different types. And every country usually has a network of measuring sea level at important places. And then in my case, the UK network is about the same size as the network you have here in Mexico in total. In the UK itself, we have 45 stations around the country like this. And also in the South Atlantic, we have 9 stations on the islands and Antarctica. So we have about 55 stations. And I know that you here have the 3 main networks that you have, and in total, it's about the same size. A big difference is that this is an important one, I think, because the Mexican Navy, I think, uses pressure sensors, and that's important, very useful for measuring tsunamis. That's a problem that we don't really have in the UK. And this is the important network we're discussing today, of course, with the UNAM network. So all the data from all the networks goes into this data bank called the Permanent Service for Mean Sea Level. And our data bank now has about 62,000 years of data. This data bank is excellent. If you have students and you want a project for a student, this is an excellent data set to use for a student project. This again is the total data in the PSMSL. But the very long records are these records here. These are more than 60 years long. So there are very few long records from the southern hemisphere. This one is at Balboa. Most of the long records are in Europe, North America, Japan. Anyway, that's our website, and you can get the data set from that, and there's a lot of training information that you can get from that website. Okay, so these are now the longest records from different parts of the world. So Brest in France, San Francisco, Bombay, Sydney, Honolulu. Takoradi is in Ghana, in Africa. So all of these, as you can see, are going up. So simply that's why we believe that sea level is rising. There are many analysis problems, but almost all records are going up like this. And you can combine them. So here are three analyses by three different people. It doesn't matter which people. So this is how global average sea level has changed in the last 100 years. And it's gone up by roughly 20 centimeters. Sometimes the rate of rise has been faster than other times. This is much faster than there after 1960. But now it's also going up quite fast. Now this record looks very like the temperature record. If you look at the global temperature record, it will also show an increase in the 1920s, 1930s, and an increase in the last 2 decades. But yeah, so global sea level is going up pretty much like global temperature. So global sea level has risen, some conclusions, has risen by about 18 centimeters during the 20th century. An important question is, okay, so it's rising, but is the rate of rise increasing? In other words, the acceleration. And the answer is yes, if you consider rates between the 19th and the 20th century. And what we really would like to know is, when did these higher rates begin? If you take, okay, look at longer timescales now, and the trouble is that we have very few continuous instrumental records from the 19th to the 20th century. Most of them are in Europe. So you can take, these are the 6 longest records in Europe from about 1700. Amsterdam, Brest, Sheerness, that's in the south of England. Stockholm, Swinemünde is in Germany, in the Baltic, and Liverpool. And you can just about see, I hope, that there's an acceleration from the 19th to the 20th century in each of these records. It's not very much, but it exists. You can also make maximum use of historical short records. And for example, in the 18th and 19th century, there are many people who went around the world, like James Clark Ross, measuring sea level for about a year, 1 year only, in different places. And he was encouraged very much by von Humboldt to do this. And he measured, for example, sea level in the Falkland Islands, in Malvinas, with respect to this mark here, for about a year. And this is the record of that measurement. So we've been able now to combine this measurement of Ross from 1842 to modern measurements. And again, you can see that the recent data is increasing faster than the average over the last 200 years. It's not very good, this, but it's something. It tells us something. The third way is to use salt marshes, and this may be very strange. But here is a salt marsh from Maine in the United States. This is at high tide, and this is at low tide. Now you can go to this marsh, and you can take a core through the top of the marsh, like so. And this core here, you can look at the composition of foraminifera, which are a type of plankton, as you go through the marsh like this. And if you can date them as well, you need to know the date of the distribution through the marsh, like this, through the core, excuse me, like this. And also you need to know how the composition of the foraminifera changes as you go up and down the marsh. Now this is a bit complicated, but you can actually, from this, look at the composition in time as you go down like this, and compare it to the composition in space like this, and you can learn how sea level has changed in that time. So, for example, here are some salt marsh records shown in at these places here, on the map here, shown in black. And again, you can see this is actually, I think, from Canada. And this, you can see here that the salt marsh seems to go faster in the last few decades than it did before. This one here is from the United States again. And again, this is the salt marsh record, which seems to accelerate at about 1900. So this is consistent with the tide gauge information in showing us that there is an acceleration from the 19th to the 20th century. So sea level is not just increasing, it's accelerating as well. Okay, the next thing is, do we understand the 18 centimeters of the 20th century sea level rise? And the short answer is climate change. And we now understand this better than we did a few years ago. If you look in the IPCC fourth assessment report, this was an attempt to explain the observed rate of rise. Just look at the blue. Look at the blue boxes. So this is the sea level rise from 1961 to 2003, and these are the observed rate of change of sea level in that time. So you try to explain this by what different mechanisms. So, of course, the world is warmer, so water will have expanded. That's thermal expansion. Glaciers and ice caps will melt. That's one contribution. Greenland, Antarctica. And then this is the sum of these blue boxes. But you see that box, well, it's similar to that box, the observations, but it wasn't very good. Now, this was 6 years ago. Now there is much better agreement. Again, this is the black is the measured sea level change for the last 100 years. And these separate curves are the contributions to that sea level change. So, for example, this black line here, that's the glacier contribution to sea level change. So all the glaciers, many glaciers, as you know, are melting. This is the Rhone Glacier in France in 1900. And in 2008, it's up at the top here only. So that black line is the glacier contribution. And then you have thermal expansion, a contribution from Greenland, and etc. And then the total is this red line. So we're now doing quite a good job, I think, of understanding why sea level has changed. Now that's the last 100 years, but the last 7 years have been fantastic. We now, in the last few years, we have a much better worldwide measurement capability. We have continuous measurement of sea level from space by satellite altimetry. We can measure space gravity very well indeed. Space gravity tells us how much mass is in the ocean. And then we have the Argo network, which tells us how thermal expansion is operating, how warm the ocean is. So we have measurements of sea level from satellites. The first one was good one was Topex Poseidon, and since then there have been a series of the Jason missions. And that produces this curve like this from 92 to now, approximately. So sea level has been increasing at an average rate of about 3 millimeters a year in the last 20 years. And this is actually went down here. This is the La Nina, which of the last few years that you see here. And it went up here. This was an ENSO event here in 96, 97. But on average, it's gone up about 3 millimeters a year for the last 20 years. Now that change of sea level can come from ocean mass, it can come from new water, or it can come from the same water which is being heated. Now to measure the ocean mass, we can use satellite. These are the GRACE pair of satellites like this, which have been a fantastic mission. But to measure the heat of the ocean, simply the thermal expansion, this is the network of Argo floats, which there are 3,000 of these now in the ocean. And they continuously measure the temperature of the ocean down to about 1,500 meters with a repeated, they drop down to 1,500 meters and then they come up again, and then they report their data back by satellite. So this is really fantastic system. So this is the change since 2005. This is the change of sea level measured by JSON 1 and 2 in black. And the ocean mass component measured by GRACE is this red line. And the temperature, the thermal components of the ocean is measured in dark blue. That's this line here. You add these two together and you get this light blue line like this. So we're now doing a very good job of understanding why sea level, why the black line is the way it is. So what we want to do is to continue this for the next 100 years. And okay, the next topic is extreme sea levels. I've shown you there's been a change in mean sea level in recent years, but have extremes change differently from what you expect from a rise in mean sea level? And that's all the public wants to know, that the public are not scientists. They don't care about climate change, and etc. But the public want to know if their house is going to be flooded, and practical things like that. So they really are only interested in extreme sea levels. So there are some famous floods from around the world, of course. Every 50 years or so, the east coast of England is flooded with a storm surge. Last year, New York was flooded with Hurricane Sandy. And in Bangladesh, it's flooded every year, or pretty much. So it's a very important subject. Now, this is quite complicated. I don't want to take too much time with this, but very briefly, if you look at this map at the top, in red, this is where we believe that the measured extreme levels have been increasing since about 1970. And in blue, these are places where the extreme sea levels have been decreasing. So you see, and in white are the places where the extreme sea level has not been changing. It's been constant. Now you see that most of the world is red and not blue. So the extreme sea level has been increasing. But if you try and allow for the fact that mean sea level, the average sea level has been changing also, and you try and remove that factor, that problem, then this map becomes this map like this. So most of this map is now white. In other words, we can explain the change in extreme sea levels mostly by the change in mean sea level. And this is a very important result. The other thing we can look at is how often, not the height of extreme sea levels, but the frequency. And so this is the rate of change of extreme sea levels above a certain threshold for the last 40 years or so. So these places in red, these have been experiencing not just bigger extreme levels, but more frequent extreme sea levels. And the ones in blue have been experiencing less often extreme levels. But again, if you allow for the change in mean sea level, then this figure becomes more like this one. It's not as red as this one used to be. And this is now, therefore, we can explain the frequency, the rate of change of extreme sea levels, primarily by mean level. Why is this important? Well, we have therefore no convincing evidence for extremes rising in magnitude faster than mean sea level. And we have no evidence for large-scale changes in the frequency of extremes when adjusted for mean sea level. And this is important because predicting mean sea level is difficult enough itself. So if you look at the predictions for sea level for the next 100 years, okay, this is the old data here. This is from tide gauges, like the UNAM network, up to now. And these are predictions here from general circulation models, climate models. And these are predictions from so-called semi-empirical models, which are what a good physicist would do, but are not rigorous in the sense of a coupled climate model. But you see there's an enormous range of predictions here. These are, if you want to design a sea wall or build a house or something, these predictions are useless. And this is mean sea level. So if the change in extreme sea levels was worse than this, it would be impossible. We couldn't predict the future. So if you're an engineer, suppose you want to protect London with a barrier like this, or suppose you want to protect Rotterdam with a barrier like this. How big do you build the barrier? You need to know how the changes in extreme sea levels will change for the next 100 years. And it's very important that we understand why that is. And at present, we believe that extremes are changing pretty much like the mean sea level. Okay, so I'm going to look to the future now, and on a more optimistic note. And in the last few years, there's been recent progress, tremendous progress, in monitoring sea level worldwide. And thanks to people like the UNAM network. So if you make a map of the situation in the late 1990s, and this is showing in blue the places where we had good tide gauges reporting in real time, doing a very good job. But you see that most of the world outside of the Pacific was not blue. But now, if you go to the present day, this is actually 2009, but most of the world is reporting data pretty much in real time. I don't know if these are yours, Jorge, or are these the Mexican Navy?
No, these are
okay. Oh, right. Okay. Right. Okay. But anyway, most of the world, a large part of the world, is now blue here. So the data is now available instantly if you want it. And in parts of the world, which in the late 1990s, you see Africa was nowhere in Africa had good sea level measurements in the late 1990s. But now there are many places where sea level is being measured very well, thanks to programs like GLOS and Odin Africa. So these are, for example, sets of radar gauges which have been installed recently. And this is one of ours, actually, in collaboration with the people in Alexandria in Egypt. This is Alexandria Harbour. This is an OTT Callisto radar gauge, which is working very well. So that's very good. That's very good news. And of course, this has benefited from, in the Indian Ocean, from the tsunami in 2004. And one result of the tsunami is now the Indian Ocean has a fantastic sea level system. And you can see all these tide gauges which are measuring sea level instantly. And another development is the use of satellite transmission. So you can use now phones, cell phones in many ways, But again, like Alexandria, this is a radar gauge. This is actually in Liverpool. Again, this is a Callisto. And there's a cable goes to this box. This box has an antenna, and this gives you broadband coverage. This gives you a third of a megabit data transmission anywhere in the world. So there is no reason why you can't transmit your data over the internet, basically. Now, all that data goes into this website, which is in Ostend, in Belgium, and that's the address you can see there. So after this meeting, you can go to this website, and you can find your favorite location, and you can see what sea level is doing. Okay, so the conclusions from the talk. We now have a much better understanding of the mean and extreme sea level changes of the past 100 years. We also have a much better, vastly improved monitoring system from space, from tide gauges, and etc. Does that mean that we have we're better at being able to predict the sea level changes of the future? And actually, if I'm honest, I don't know. I have no idea. This isn't clear to me at all, because predicting the future is always difficult. Even if you have perfect, very good computer models, to actually say what's going to happen in 100 years is really very difficult. But I do know, the one thing I do know is that if we are going to produce good predictions at some point, then we need to understand the reasons for sea level change. And so we have to measure it, continue to measure it as much as possible. We need continuous access to all the data sets, but in particular, we need to maintain the monitoring networks. And so that's why I'm very pleased to be here today, because the three networks in Mexico are critical to provide the data that we need. Plus, of course, Mexico cannot do it by itself. It has to have international cooperation. Okay, so a lot more about this stuff is in a book, which I think you have in your library here, which was written a couple of years ago and is now an e-book. And this can tell you more of this subject. Thank you.